I will talk about an estimator that is a mixture between a particle filter, so a probabilistic estimator, and a set membership observer based on interval analysis. Let's talk about the application. We're interested in an autonomous aircraft that flies navigating using an inertial navigation unit that provides at each time step position, velocity, and altitude, but this sensor has a drift, and after a certain time of flight, the drift implicates an error that has grown, and the estimation accuracy doesn't fit with the mission requirements. And for example, here we can consider in terms of position an error such as 1 kilometer. So we have to correct that, and usually we correct the IMU, the inertial sensor, regularly using, for example, a GPS receiver, and that is a typical way to do an accurate correction. But here we consider that we cannot use the GPS because it can be denied, it can be jammed. So we consider an application where we use terrain-aided navigation. We embed a digital elevation model map of a given area that we plan to fly over. And so it contains the elevation of the terrain. And we want to correlate those embedded data with a very simple measurement, that is the relative elevation MK between the aircraft and the ground. So we have to develop an algorithm that correlates those data to rebuild the state, the navigation state, position, velocity, altitude, to correct the navigation estimate. So we have to get an algorithm that is robust to strong nonlinearities, because the terrain is usually very nonlinear, and it is also non-analytical, because it is a map that we embed. It has to be robust to ambiguities. Nothing is more similar to a mountain than another mountain, so we have to cope with that. And we want to embed it, so it has to have a low computation cost. An approach that has been explored in the literature is the particle filter. A particle filter is a probabilistic estimator that draws a cloud of possible states that are called particles, and they are weighted by their probabilistic likelihood to be close to the real state given the measurement. And iteratively, we can resample this cloud of particles to converge around the real state using the successive measurements. However, in practice, here is a very ambiguous terrain. It is a real mountainous terrain. It is in the Alps, and it is viewed from the top. We have a canyon. It is quite ambiguous because it's quite flat. And we have ambiguous mountains and valleys. And the green line is the trajectory we want to follow, and we want to estimate. It is the real trajectory that we want to estimate. And we start with a given uncertainty area. And what we could get with the particle filter is something like this. The red line is the estimate. It diverges because it cannot remove the ambiguities. So many works have been, even if there are several thousand particles, many works have been done to robustify, to make particle filter robust, but most of the time they were heavy to compute, and we cannot embed some heavy algorithm. So we searched for some other approaches, but still related to particle filters, and we found something very interesting in the literature. That is a box particle filter. It is a particle filter that replaces each control particle with some boxes, some vectors of intervals. And it's very interesting because it uses interval analysis, and usually interval analysis operations are quite simple, numerically simple to implement in an embedded hardware. So it follows the same steps. We initialize using a paving instead of drawing a cloud. We dynamically propagate the boxes according to a dynamical model. The measurement is supposed to have a bounded uncertainty that is useful because in our case, it is difficult to have a very precise idea of the density of the measurement. It depends on the ground you are flying over. And we have what we call a resampling step. We remove the inconsistent particles to replace them with particles, with consistent particles. It was not dedicated to navigation. We tested it in our application, and so the principle, the goal is the same. We want to converge around the real state. About the way of weighting, because each box is a bounded set, but it is also weighted by their likelihood to contain the real state. And here it is done using a ratio between their contraction, because there is a contraction thanks to the bounded measurement, and the likelihood is very easy to compute because it's a ratio between the volume of the box before and after. So it's numerically simple. And we tested it in our application in the same scenario, and we've got something like this. In fact, we get something very robust, but not accurate enough. It doesn't diverge, but it doesn't converge enough. And but it was a good start because it is fast to compute. But we wanted to add some accuracy to this algorithm. And we derived it to propose a new version that we call the box regularized particle filter. In fact, we added some step in the resampling step. The resampling step is removing the inconsistent particles to replace them with consistent particles. It is not operated at each time step. It is It is triggered regularly if there are too many inconsistent particles. And we propose a combination of two strategies. The first one is about the way we replace inconsistent particles with consistent particles, and the second one is a kernel regularization taken from some probabilistic strategies. So the first step we had is about geometrical subdivision, because when in the initial box particle filter in the literature, it is proposed to remove inconsistent particles to replace them with subdivision of consistent particles to increase the resolution of the exploration of the state space. But the problem is how to subdivide a particle that has several dimensions, and here we have 15 dimensions. We have to, it's proposed in the literature to choose dimension on each box to subdivide it. But it is difficult to choose appropriately this dimension. Several solutions have been proposed. For example, randomly picking one dimension, because it is general. We can subdivide around all dimensions if we consider the whole box particle cloud. But the problem is that it is not really optimal, because we can end with badly proportioned box particles. So we proposed a normalization method to get some well-proportioned box particle, and also to normalize, because we have several physical dimensions. We have position, velocity, attitude. It is difficult to compare them, and what we propose is normalizing them to get the larger side of the box, and the larger side after normalization needs to be subdivided. This helps to end with a well-proportioned box. And the second solution that we propose to combine with the previous one is the one I want to highlight here, because it is taken from another community, and it has been proposed to enhance a probability density function estimation that we estimate with, for example, several points, several particles, and it has been applied to refine conventional particle filter estimations, and we derive here it to apply it to the box particle filter. And it consists of shaking the box particle supports using a bounded probability kernel to get something more accurate. But we tested that without knowing if it would bring something better. And we were very surprised to see that the results were more accurate. And we found an explanation. Here is an illustration of what can happen before regularization and after regularization. So here we are in the resampling step. The subdivision step has occurred. You can see that. Because we have removed some inconsistent particles and replaced them with subdivision of consistent particles. There are the blue remaining particles. But we have something well organized. It is a set membership organized estimator from a regular type. And after regularization, of course, we moved the box supports with probability kernel. And we've got something more smooth and knowing. So what is the meaning of that? If we plot an approximation of the posterior density function, the posterior density function represents the likelihood for each point of the state space to be closed to the real state that we want to estimate given the measurement. And here it's just plotted on the two first dimensions, latitude and longitude. And in the box particle filter, we can approximate this density, this posterior density function, by a weighted sum of uniform. We can consider each box particle by a uniform density function whose support is the box itself. It is an approximation that allows to make the link between the interval analysis observer scheme and the probabilistic observer. And before regularization, we have something, as I said, very organized. You can see that you have some peaks, some higher points. So the estimate, the estimate will be around the higher points. That means that the real state might be around those points, but it is quite rough. It is quite jagged. And if we apply regularization, we get something like this. We have something that is smoother, and we can more accurately get some peaks, some maximum, and we can more accurately estimate something close to the real state. This is only during the first iteration, but after that we have the same, at each resampling step we have the same process. And on the previous example that I've shown, we can get something like that. You can see that the box particle better contract around the real state. More efficiently, they get well proportioned, and we've got something like a better precision. And we only need 200 particles. And for a typical particle filter, it is several thousand. The Baylor case that I've shown at the beginning was done with 5,000 particles. So this is only one run. It is an illustration to show you what we can get, what we could get in real life. But in terms of Monte Carlo simulation, we have done the estimation. We have repeated this scenario 100 times with different measurement noise, etc. And here is the root mean square estimation error that we get with the box particle filter, the initial box particle filter from the literature. We can see that we converge, but we reduce the error across time. But the accuracy, the average accuracy is not so good, but that was the beginning. If we add the first strategy I've talked about to get well-proportioned subdivision of the box particle during the resampling step. We get something like this. So it is better at some times, but we end with the same root mean square error. So it can bring some good things, but it is not sufficient. There is something missing. But if we apply regularization, we get this. We end with a root mean square error that is about 100 meter in that case. And 100 meter is the resolution of the digital elevation model map we use. So we cannot reasonably expect much more. So we have here a significant enhancement using some probability schemes that we link with some interval analysis schemes. We also implemented it on an embedded chip because we wanted to demonstrate that it is possible to embed such an algorithm. And we used an FPGA, and we wanted it to run at least at 10 Hertz. And in fact, we can, with much more particles that are required in practice to converge, we can run about 70 Hertz. So it can handle real-time applications. So to conclude, we have developed a derivation of the box particle filter, that is the box regularized particle filter, that takes advantage both of set membership interval analysis approaches that bring robustness and probabilistic and stochastic theory that brings accuracy. Because it seems possible to link those tools, those mathematical tools, to get something robust, and inside that robustness to try to converge more accurately. In fact, from a probabilistic point of view, it would be manipulating the bounds of some bounded probability density functions. And from the set membership point of view, it would be manipulating some set bounds and then trying to estimate what happens between those bounds. And we also implemented it to see if it was possible to handle real-time applications. So thank you very much for your attention. If you have questions, do not hesitate.
Yeah. I'd like to know how one may choose the size of the kernel window in order to achieve the optimal performance in terms of what you said of discovering of the probability density function. What is the best size to choose? Because you showed us there something, but what's the size of the kernel window?
For the initialization, you mean?
Yeah, regularization.
Oh, yeah. Do you mean the kernel, the bounded kernel length?
Yeah, you apply a kernel.
Yeah.
Okay.
Yeah, I apply a kernel.
What is the size of the window?
In fact, it has been demonstrated in it is a book by Silverman, application in general, and has been demonstrated that in the case that every weights are equal, and that's the case because I didn't mention it, like that in the resampling step, the weights are reset to the equal value. Every weight is equal. So in that case, there is an optimal kernel that is a Nepomniachtchikov kernel, and whose whose length is also defined by theory. So I don't remember the exact formula right here because it's quite complex, but it exists, and you have normally you have the reference and you can find
You have the reference here?
Yeah.
Yeah.
It is also
It's not
mentioned.
clear. I mean, it's okay. You show a spectacular result, but it's not clear what's the size of the kernel. I mean,
Yeah,
you say you apply an optimal, you choose an optimal, compute an optimal size of this window, but how is this done? This is my question.
It is done here. We compute this regularization, assuming that just considering the center of each box particle. And the length of the optimal kernel is obtained computing the difference of between the theoretical density function we can have and the approximation that is here, sum of that time Dirac density function centered on the center of each box. And this is called the MISE, the mean integrated square error. And by minimizing that, you can find some appropriate kernel and length.
Okay. Thank you.
Any other questions?
If I understand correctly, I mean, somewhere in the algorithm you do like shading or the box or something like that.
Yes.
So it reminds me of a shaving procedure in programming. Or in other words, it looks like you are removing some part of the boxes.
That's true.
And then for something that you still cannot explain, it works better and so on.
That's true because we, at the beginning, but the theory, this works for punctual particles. It has been demonstrated. And here consider that we do not change the size of each particle while shaking. But the theory would, well, we initially thought that it would be, that we would have to draw on the boundary of each box particle to shake the boundary without moving the center. But in fact, it doesn't work. I don't have the answer to everything, but among the tests that we have done, not changing the size is the best way, but it is also linked to the poor observability we have on this problem because remember that we're interested in very, very ambiguous problem. We want to estimate ideally 15 parameters, and we only have half of one parameter of the elevation that is observed with some certainty and some linked uncertainty. So maybe we have to be careful moving the length of the boxes, and maybe in other cases it would work better. In that case, and we also tested other case, similar case with some math, but other kind of observation equations. It still provides better accuracy.
So if I could summarize, in fact, although it's a box particle filtering, it seems that somewhere in the algorithm you're still working with the center of the box.
Yes.
And that's why your shading procedures, in a way, makes the center to explore new areas and hopefully give better results.
Yes. Yes. But we also remove some parts of the space that were explored by the box itself. But I think we have to stochastically think also because we have several hundred, box particles, and what we can see on this illustration is that something that is not covered anymore by a box will be maybe covered by another. So it is kind of a stochastic and also a little bit pessimistic exploration. So does that answer your question?
Yes.
What if you use the typical parts and window approach?
Pardon?
What if you use the typical parts and window approach? What would it give?
In that case,
Yeah. Yes.
Um,
You have a digital elevation map.
Yes.
You have 2 dimensions.
yes.
So it would be an easy task to do to pass the map with the person window.
Yes, I see what you mean. Here we
What
go.
would it give in compared to your approach? I mean, this is.
I didn't test it, deterministic estimator because we were interested in dynamic, also in studying the dynamics of the problem. So we have also some uncertainties in the dynamical model that come from velocity, and the velocity is also impacted by the attitude, that is also impacted by the angular rate measurements from the local sensor. So we also want to take into account all those dynamical uncertainty propagation. So maybe a deterministic approach would be not able to handle such a high dimensional problem, but I don't want to make some I don't know.
Okay, I haven't worked with this type of box particles, but I mean it's the same with shard optimization. It's much more difficult to prove that it converges somewhere.
You're totally right.
You need the proof is only in probability. You never know if it will effectively work.
That's true, and in fact,
compared to optimization with interval methods.
Yeah, but we wanted to see if mixing some probability approaches and set membership approaches, if we could have something robust and accurate and fast to compute, because there is an industrial application behind, and but so it's true that it could it's also true that for a conventional particle filter, it is very hard to make some convergence proof. You can bound the estimation in theory. You have some tools to cope with that, but you cannot have explicit proofs. Thank you.
Anybody else? Would you like to explain briefly how you moved from 5,000 to 200 particles? Was it for efficiency reasons or?
We wanted to have something that is less computationally costly as possible. But here we can move from 5,000 to 200 thanks to the box, to the box particle concept itself. A box particle will explore a whole region of a whole area of the state space. And a punctual particle only explores one point, and that is a problem. That's why the particle filter is not robust in such a case, because we have very ambiguous and it's also locally ambiguous problem. And with a box, we can explore a whole area. So we have a higher level exploration. And the second reason is that the intersection and likelihood computation operation are very simple. Very simple to compute in terms of numerical implementation. To make an intersection, it is on a hardware point of view, it is only two wires that have to cross, but it is simpler and also helps to reduce computation.
Thanks very much. Let's thank our speaker again.